Hi everyone, welcome to week 9 and our today's Christmas special. I'm happy that you're here today. And with me here should be David.
Hi. Yeah, today in a little bit strange setting again. Nice snowflakes, Alex. How do you do
Thank
that?
you. Yeah, we started a bit later today since I saw that you and Micha are having snowflakes and I also wanted to have snowflakes and so we did this last minute. Looks kind of nice, I would say.
Yeah. So I hope you can hear us well. Is the sound okay? Because we are again in a different setting today. I think we never had the same setting in 2 or 3 times. This is always different. Sound is all right. Yeah, thank you very
Sounds right,
much.
that's good, that's good.
Yeah, so I'm at home. I'm in isolation. Alex, you're in Upper Austria, I think.
I'm in Upper Austria, that's right,
Yeah,
yeah. So different settings, but I think for the last week this is also okay.
great.
Okay, yeah, what are we gonna do today? We will talk also a bit about trees, similar to what Julia did today with you. And yeah, basically we have some topics that um, should repeat the whole data structure part and also somehow connect to the linked lists we did last week. And we also have one or two special topics today that we haven't covered in the lecture as a whole, but today we just want to briefly mention these concepts, two concepts that you probably have already heard or have seen in other lectures, but now today we want to talk about them officially.
Yeah, I
Yeah,
think I think you should change the OBS scene.
yeah, because I prepared a very nice Christmas themed paddle
Yeah,
slide today. All right, so short recap. In the last week, we talked about linked lists basically, and we had this homework two shock where you worked on lists. And last week we talked mainly about a linked list as a song playlist kind of artist's title length. And what we also had was a reference to the next song. And so we built actually a linked list and we did some coding last week related to that. And here you actually can see this list that we created last week. So we had first element, follow-up element, and each element points to the next one as long as there is a next one. And if there is no next element, the element is null, which means this is the end of the list. And to have the value null in the next song helps us to find actually the last element. And this is very useful when we want to go through the list and search something or add something, delete something. So this helps, and this is like a good characteristic of what our linked list should look like. We also talked about binary trees last week, and here in particular, we had a very rough concept of what it is. Julia mentioned that in detail today. We have an element on the top, which is called the root element, and the root element has two children, a left element and the right element. And so we build actually a tree based on this characteristics that each element, each node can have a left and the right element actually. And so we can build a tree.
yeah.
Yeah,
This is a slide from a few weeks ago, I think, where we talked about memory layout. But I just want to mention it once more because we you came to another small topic. So this is maybe the last slide from the recap here, which then goes into my or an interesting topic. Um, here we talked about the memory and the memory layout. I think it was 4 weeks ago already. We had local variables and the address of stack variables, the heap variables, constants, and we also had in this last printf the address of a function, and we saw that also a function has an address because it's somewhere in our address space.
Right.
And this is interesting because also functions can have addresses. And when we remember, a pointer is just holding an address. So the value of a pointer is an address, which means it might be possible maybe to store the address of a function also. And we can do that also. So we can really make just like pointers to functions, and they are called function pointers. Alex, may you go to the next slide, please? Thank you. And I know these function pointers are, they look very strange. So I want to give you step-by-step guide how you can read it. So let's suppose we have something like this. We have a print function, and the print function has an address here. So we can take the address from the print function, and we want to store it, let's say, into a void pointer like this. And then we call this function. This does not work. We get an error when we do it like this. So maybe we can add parentheses, so brackets to the pointer. This does not really have an effect. Alex, one more, please. Yeah, thank you. So this is just the same as before, but we need it when we write or when we create a function pointer. But this again results in an error because it says, okay, it is just a function pointer. We need just 2 more brackets there after the definition of the function. So this is the correct syntax, and I know it's a little bit hard to read, but we take the address of the print function and store it in a pointer, in a function pointer, and then we can call this function pointer. So when we execute something like this, we will get then the output of the printf. And we can also create parameters, for example. So if this print function has some parameters like this, we can take the address again, we can write it into a pointer variable, and then we can call this pointer, or this function pointer, as it would be the normal print function. In this case, it doesn't really make sense, to be honest, but it's just one step closer to my next example, which might be a little bit more interesting. So this is the normal way. There are no function pointers inside currently. We have a main function. We have myfunc, and this myfunc function then executes the print function with the value 5, for example. And we can use function pointers there to call this myfunc. And then we hand over just the function. And we take in myfunc as an argument the address of the function, so the function pointer. And then we can execute the function inside. And this gives me more flexibility because I'm now can, in the main function, for example, decide which function I want to execute inside a specific function. So in ESP, I don't know how you see it, Alex, but I think in ESP function pointers, you do not really need function pointers. It might be possible in some cases, but there are advanced topics in the upcoming semesters where you would need function pointers, right?
Yeah, I agree with that. We will need it today since I prepared an example where we would need it. a typical application is in sort functions where you actually give to the function a function which says how you should sort something. So this is a very typical thing. But we won't cover this here in detail. So at least you have seen it and you know that there's something like function pointers. But at the end of the day, you will need this in many other lectures as well. Yeah.
Yeah. All right. That was already the background from function pointers. And as Alex said, we will need this in the coding task Alex prepared for us today. But at first, I think the second Christmas tree you will see today, because also Michi and Julia created a Christmas tree. Ours is a little bit different, I think, but let's
It's a
see
bit different, yeah.
What have you prepared for us, Alex?
So actually,
sorry. I just saw that one question came up in the chat. Are this function or this function pointers like callback functions? Yes, it is really like a callback function. So you can provide a function and then inside a function it can execute. So callback functions are like this. Yeah.
right. Okay, so I want to discuss with you just briefly the structure of our Christmas tree, step by step, so that you can see all parts and ingredients of the tree. So actually, at the upper point, we have the so-called root node, which is actually the root. We can just have one root node, and then we have different levels. And the overall number of levels is the so-called depth. So there's like the depth of the tree. And in our case, we have 4 levels. So level 1 is the root element, or the root node, and then we have level 2, 3, 4, and this can continue, and in theory, infinite number of times. We have a so-called parent node, and a parent node can have a child node. And for example, the root node would also be a parent node. It would be the parent node for 2, and the child node would be in that case 2. I hope this makes sense. So that in that case we can like switch with parent nodes and child nodes. For example, here 15 is a child node of 12, but it's the parent node of 17. So especially in trees, we always have this terminology with parent and child. And the last nodes, like the very last layer, level 4 in our case, it's just one node, but it's called the leaf node. So it's the very last on the very last level. When speaking about a tree, leaf, blood would be at the very end of the tree. So that's the idea of how our tree is structured. And now let's go into detail and see how we can build a tree like that. And let's assume we have the sequence and we want to store or want to build the tree to store all these numbers of the sequence. And in that case, let's say, okay, we want to add the number 6.
It's great that we cover with our camera exactly this on the top right.
Yeah, that's not really smart actually, but what I could try is to move us.
Oh, I think it's just 6 there.
Yeah, but there will be a few things. So I just moved us. Now we're behind the coding. I think it's good for now. So maybe just short message in the chat if it's okay now for you. Or David, do you see if it's okay? Should be okay, right?
It seems okay, yeah.
Yeah, okay. All right, so we want to add, and for that reason, we start building a tree. So our root element is 6. That's pretty easy. Let's continue with 2. So we want to sort this tree already. So this is a very easy idea. Everything which is below 6, like 0 to 5, should be on the left side, and everything above 6 should be on the right side. So when we add 2, 2 is smaller than 6, so we just add it on the left side. Now we have 12. 12, the number 12 is larger than 6, so we add it on the right side. Then let's continue with 1. 1 is less than 6 and less than 2, and so we put it on the very left. Let's continue with 4. 4 is less than 6, so we go to the left, but it's larger than 2, and so we have to put it on the right at the end. We continue with 11. Same principle. 11 is larger than 6, so at least once on the right, and smaller than 12, so we put it on the left. Same with 15. 15 is larger than 6, so go to the right, larger than 12, and to the right again. And one last time with 17, and I think it's clear in which direction this might go. Larger than 6, larger than 12, larger than 15, and so we put it as our leaf element, leaf node at the very right. So in this way, we build a tree, and that's actually the entire magic behind that. Are there any questions regarding that? Or David, do you have something that you want to add?
No, I think it's so. Michi and Julia, especially Julia, also talked about this concept in another terms, but this is a great example how you can also sort by just inserting in a tree. So as you can see here, when we read from left to right, it's already sorted. And of course, when we want to print it, maybe you will do it in a few moments, but then it's a little bit interesting to see how we can sort it and print it sorted. But yeah, it is always nice to have a visualization like this.
Yeah. And online there are billions of tools which you could use also for visualization. And it depends, of course, on the sequence and the ordering of the sequence, how the tree looks like. So this sequence could look completely different if we start with 1. In the worst case, we could have a linked list actually, and this is what we don't want to have, because the cool thing about the tree is actually when it's well balanced, then we have an easy time with the tree. But if it's not balanced, then we have actually a linked list, and we don't want to have this because we want to have a tree. There's a question in the chat. What about node splitting and deletion? And we could do this as well. We could ask ourselves, okay, what should we do now, or what would we like to do if we want to delete one of the elements, and how to rearrange the tree. Actually, what always would be very easy is to delete like the leaf or a leaf element, because here in that case we have to find 17, just delete it, nothing will happen. But let's assume we want to delete the root element, so then we have to think about a way how to restructure our tree actually. If we decide to delete 6, we would have 2 potential root elements. We cannot have 2 potential root elements. So we have to decide how to restructure, how to rebuild our tree in a way that we can manage that. Or if we delete 12, for example, how should we rearrange it? Would be 11 the following element? Would it be 15? Where would the other element be? So from a programming perspective, this is quite similar to how it is when deleting in a linked list, because we should keep in mind always the parent element, and then we can actually take this element and connect it to other elements as well. But yeah, it depends a bit on what we want to do with the tree and how to restructure it.
Yeah, in general, I think we always want a balanced tree. So balanced means there is no, so it is not just one way, way down, and many leaves, or the depth, many levels in one node. So we want our tree balanced in general, and if we, so this is more advanced topic, but if we see that our tree is somehow not balanced, we could rearrange them and change the nodes so we get a balanced tree again. But this is a common problem, which I think it's too hard for us to discuss now. It will be discussed in the next semesters.
Yeah,
But
you will do a lot of that in the data structure and
yeah,
algorithm subjects, and this is a lot about graphs and trees, where we'll talk about these problems. But yeah, I mean, these are well discussed problems because these are problems that happen in day-to-day settings all of the time. So it's a tree and a graph are very well-known data structures and well-used data structures. But from a C implementation standpoint, you would have in theory all the knowledge to do some things with it.
and also in the chat was the question about file systems. So file systems are implemented as a tree in the background. And they also have, of course, the problem, but you will get into this, how file systems are structured in operating systems. So I won't spoiler too much. It's very interesting how they structure files. So you can have something like infinite sub files or subfolders, and it should always be somehow balanced. But it's very cool how they do it.
Yeah. Okay.
All right.
Yeah. Actually, that's the Christmas tree or the idea behind that. And now I want to do some programming. And now I want to make a program which is actually more or less a list of stuff which we think about Christmas. So when you think about Christmas, what is like the first idea that came up? And then we will build a tree with all of these words and try to have a balanced tree, and find some of the words then in the tree. So we will play around a bit with that one. So just type in the chat like words which you somehow relate to Christmas.
I think you can then drag us up again into our box.
Assignment 3. Oh my god.
Alex, I think you can drag us up again into our box.
Just did it.
Okay, yeah, great. Perfect. A little bit more, I think.
Yeah, just right. All right.
Great. Now it works. Snow.
Okay.
Yes, snow would be also interesting, but unfortunately, it's not always when we have Christmas. Food, yeah.
Okay. We have cookies. We have family. We have assignment 3.
For
So
me,
no,
it's
present.
Vanillekipferl. I don't know the English word for that.
Good in German as well. Advent of code. Cool. Bananas.
Can you make it a little bit bigger, please?
Of course.
Yeah, great.
Too much.
That's great.
Oh, yes. So, okay, vanilla bananas. Okay, I think we have at least 9 of the words. That's okay. So let's save this. And let's say Christmas list. Okay, so Yeah, cats is a good point. Let's add cats. I prepared just a very rough skeleton here. And yeah, we agreed that we want to have some like Christmas terms, kind of. And yeah, so this is like the base for our Christmas tree. The question now is, where should we store it? So actually we have one character and we should have a node with a left and a right element. And I mean, very obvious question. And I think we'll all agree that we want to have a struct therefore. And for that reason, I will create the struct. And let's type dev the struct already and say we call it, I don't know, ornament. And I mean, I should probably deactivate my copilot, but we have a name with the 50 elements. We have a left element. We have a right element.
What is ornament in German? Just in case. It's like I don't know, Schmuck or Verzierung, or how would you say?
The ornament is like the Kugel am Baum.
Ah, yeah.
That was my idea, like, yeah, having a nice decorated tree, actually. So yeah, that should be the struct with everything that we need. And yeah, now we will create the tree based on that. And ornament is also a German word, that's true, yeah. Okay, so what should the tree actually do? We want to get the words from the Christmas list file. We want to set up the tree. We want to search something in the tree, and we want to insert something in the tree. This is actually what our program should do, and we want to free something if we have still time. Therefore, since we didn't do the free part last week, I guess.
So every line in our file should be one node, right?
Right.
Okay.
So we have one node with cookies, one with family, one with assignment tree, and so on. That's the idea. So let's say we want to start to build the tree in a way that we read line by line from our text file. So we get all of our elements from the text file, and we just write the function therefore. And actually, I would say we call it, I don't know, create tree from file or something like that. And now we can say that we pass to this function the file name. And what will we return? I mean, what would be cool if we return the tree, actually, since we say create tree, then in that case, it would be good if we return the tree, right? What would be the tree, actually? So a question to the chat, what would be the return type in that case? Would it be like a ornament or void, or what would it be, actually? What do we want to return?
So in this function, we want to create the whole tree. Okay.
Yeah, that's right. We want to have an ornament pointer. Because that makes sense in that case to say, okay, we read it line by line and create the tree already here. I mean, there are like different ways to do this. I decided for that one.
And which ornament do we return here? Just a single node?
Ideally the root element,
Yeah.
because then we have the entire like tree by just giving one link to the or one address to the root element. We store this, then we have the entire tree. We don't have to pass like a tree or whatever. We just need the first element, the root element.
Right.
Does this make sense?
Yeah, it's like the start of a linked list. In this case, it's just the root, where is the start in somehow where we can access all the other nodes then.
Yeah, maybe let's do it like that. I mean, we know that we want to have a root element, and at the end we know that we want to return actually a root element, and then everything beyond that should be just the reading from file part. So first of all, we have a file name, and since we have a file name, we can actually read the file, and therefore, let's say we will open a file, and I mean, Copilot gives me already a good hint. It says fopen file name with R. Brief question to everyone in the chat: why R? Why not W or A? Why is it R, and what is R about? Read. Perfect. Read. Yeah. Perfect. Read. What is the next step after we open a file? Again, question to the chat. It's a Christmas lecture that we can do this somehow together. Then I don't have to think too hard.
Yeah, it is also what we will do the next 40 minutes. So there is no other topic we will discuss. Just
check for null. Perfect. Perfect. Simon, you're perfectly right, and Sabaton, you're perfectly right after that. So it's like already in the rearranged order. We have to check for null first. So let's say if file is null, then we will be very sorry, and say, I mean, this is already a very good hint. Error opening file, file name, return null. Let's do this. Yeah, and the next step that we do is, as Sabatom mentioned, we go line by line. And going line by line means that we need some kind of a loop. Which loop would you prefer? Chat, what do you think? Yeah, Muhammad, completely right. Root would be actually the head of a tree. Okay, for a while loop. I would also prefer going with a while loop actually, because the condition is quite easy here. Let's say we will have while, and I could get the line actually and say, for example, f gets, then we need a buffer, which means we have to store our line somewhere. Therefore, we can actually create a variable with 50. And as we know, since I wrote 50 already 2 times, I should probably do something. Max namelen. All right. Then we have line and a max count, and the max count would actually be, yeah, the maximum of the line. And then the stream, and the stream is actually file. And our condition if it's not equal to null. Okay. So now we have a function which goes line by line. And what should we consider now in the loop? So one thing is that we have something in the line which we don't want to have in our character. Because at the end of the line, what do we have? Question to the chat. What do we have, and what should we do with that? At the end of each of our lines here. Yeah, \n, right. I would rather have a \0. And in that case, I just say the very last element should be \0 instead of a \n. That's pretty easy because, I mean, line is just an array, basically, and I want to be in the very last position, and the very last position should be replaced from \n to \0. And we can do this actually by saying, okay, we have line, then there is this function, and actually we can have a closer look at that because I don't think that we used it too much in the course. Please correct me if I'm wrong.
No, I think it's the first time, yeah, because also in assignment 2 it was forbidden to use the string library, so maybe it's the first time for most of us.
So then I would say let's do the only right thing, Google it. What is it? And why would Copilot suggest using it? Let's go to the C++. Get span until character in string. Scans string 1 for the first occurrence of any of the characters that are part of str2. Returning the number of characters of str1 read before the first occurrence. I mean, this is actually pretty cool. This means we have a string 1, and in our case, it's not a string, it's just a character, but we can use it as a string by just taking a double quote instead of a single quote with \n, and then this is our very last position. And we just try this now. So let's say we have our line, and this function gives us the position of the first occurrence of the \n, which is our last array element actually, or string element in that case. And we just replace it with \0 and say, okay, this is the end of the string actually. Does this make sense? Does this make sense for you?
Yeah, it's just we just overwriting the new line with a \n, right?
Right. That's the only idea of that. So we get the position of the very last one. We override with \0, and that's the entire magic.
So I've just one question came up from my side. What happens in the last line? Because is there also a new line, or is there the end of file before new line?
You mean what happens if we reach this line, like cats?
Yeah. So if we do it like this,
yeah.
I think there is no new line at the last line.
Yeah.
There is just the end of file then, right? So I think we have to make one new line at the end of file.
We could do this, for example.
Yeah, I think this would fix it. Or we have to consider the other case in the program, which is maybe a little bit more challenging here.
Maybe all of you doing the exam last week, or this week actually, 2 days ago, that was also some kind of a question where we had a code analysis example where the task was actually to count the \n's. And what David just mentioned is a very good point. You always have to consider this case. So one way would be to say, okay, here \n, or another way would be to say, okay, the last line would be the line without the \n, and so we have to have a different process on how to deal with the last line. Okay, anything else? Because now we would have, yeah, the first line was skipped. Yeah,
Yeah, that was the trick in this
that was the
example.
trick actually. So what we could do now for testing purposes, we could just print the line here and say if this is working overall. I mean, we wrote at least some lines of code, so then we can do some testing. Let's say Christmas list T, and then we should call the function, and that should do the job actually. Please don't kill me. I've just it's installed here. All right, we want.
This is just another compiler to CLang
Yeah,
or Clang.
I think we worked already with GCC.
Yeah.
Especially when I hosted, because I don't have a Clang here currently running. All right, then we are having the Christmas tree document and Christmas tree, and then we okay, that looks already pretty good. Here
I have a question. I have
yeah.
a question. So, in general, yeah, there's a warning because of an unused root variable, but I would think we will use it anyway in the next steps. But when you would execute it with Valgrind, would you say that there are any problems?
That's a good question, and I would like to give this question back to the chat because you encountered something which could be very interesting. So, question to the chat: is there probably some warning? Oh yeah,
Yeah.
yeah. So, what should I do to prevent this?
Yeah. We need
Right.
to write f close. Yeah. And another question was, warum checken wir in der While Loop nicht auf EOF? So in diesem Fall brauchen wir das nicht, weil fgets, also wir haben ja in der While Loop die Abfrage, dass fgets so lange checkt, bis es ungleich 0 ist und fgets returned 0, wenn es EOF erreicht. Also wir checken es quasi implizit.
Genau. Wie gesagt, da gibt es ganz viele verschiedene Möglichkeiten, wie ich an das Problem herangehen kann. Das war jetzt aus meiner Sicht einfach die ich halt gewählt habe, aber natürlich könnte ich das auch anders machen. Okay.
All right. Yeah, now it should work also with Valgrind without errors.
We can give it a try.
I hope you
I mean,
have
at
it installed.
least, let's see. Yeah. I think I have to compile with. Makes anyhow sense for later.
Yeah, looks good.
That looks good. Yeah. Okay, perfect. Yeah, what should we do next? Now we went through the list.
So did we already created that our tree?
We return a root, but have we like did something with it? I don't think so. So maybe we should create the tree now actually. And how to do this? Just reading the chat message, also ist ein Leerzeichen nicht gleich 0, weil in der the emojis are always over the chat, so I cannot see it clear. Okay, also ist ein Leerzeichen nicht gleich 0, weil in der ein Backslash n ist.
Also eine Leerzeile, ja.
Ah, in der Leerzeile, ja.
Eine Leerzeile ist immer, also es kommt drauf an. In der ganz letzten Zeile ist jetzt kein Backslash n drinnen, weil ja danach keine letzte Zeile mehr gibt. Das heißt, da ist wirklich dann nur EOF sozusagen drinnen.
Genau. The next thing that I would like to do is to insert an element into the tree. And therefore, we will write one function, but this one function contains basically two functions. First, I want to create a function which just creates an ornament and initializes it. That's pretty easy. We just call it create ornament, and it just takes the value that is interesting, which is the name. So actually, this function does nothing more as creating a new ornament for a Christmas tree. And return it, obviously. So we say ornament, and it's just like that. And whoops. And what we're actually doing is we create a new element and get it from the heap, which means whenever we want to do something with the heap, we need malloc. So that looks already pretty good. And what we will get is a pointer, and so we say ornament, new node, whatever, malloc. So in that way, we will get a new element. Yeah, why not? Let's have a null check, since we should do this actually. And now what we should do as a next step is to initialize the ornament by saying the name should be the name from the argument, and therefore we can use the string copy function or the string n copy function. Just as a reminder, the n is just the length, and this is like a security thing. If I use this here with the n, then it cannot write in any other memory locations where we don't have access to. So let's do this because it's like the more secure way. And then I also should do something with my left and right element. And yeah, I mean, we know what the next element is, so we just set it to null for now on. So we actually say the left element is null and the right element is null. And what we also agreed on is that we want to return the new node element, and we just say return new node. Okay. Now this function should just create a new ornament on the heap and return this element. And so we can insert it then in the tree. We could do this also in one function, but yeah, we want to split it and have very specific functions for very specific things. And this specific thing would be to create an element on the heap. And the next thing is to actually put it into the tree. And for this particular reason, we write a function which is called insert ornament, for example. And what we give to this function is the root element, the line, because the line is actually the term or the word that we want to use. And the cool thing now, and this is where the function pointers comes into play, is we also want to have a function. I will talk about this in a second why we want to have a function actually, but this makes sense because we can decide if we want to have the smaller elements on the left side or on the right side. So this compare function helps us to decide how our tree should be ordered or sorted actually. Does this make sense?
Yeah, so this compare here is now just a placeholder for a function we will write in the future, right?
Yeah.
And this is then the name of the function. The name of the function is like a pointer to the function, so to the address of the function, and we will implement it later. So maybe just a short comment from my side. Can you close or minimize the terminal when you're in the code view, because we have then a better overview of all the code? Yeah, great. Thank you.
Sure. Okay. Yeah, we also agreed that we will return something here, and by now we don't like write something into root, and so I would say, let's say root ornament, and in every loop iteration we will get the root element for each iteration, save it, and then we can return it. Actually, I'm pretty fine now with the create tree from file function, because now we're going line by line. Now we put each line, each string into this function. This function should do some fancy magic that we will discuss in a minute, and then stores the result here, and then closes the file and return the new tree. I think that should do the job. David, do you have some concerns with that so far?
No, I don't think so. So I think the next step would be to create the insert ornament function, right?
Yeah,
Or
that is a good
do you
idea.
want to create the compare function first? I don't know.
Let's start with the insert ornament function. We can write it actually here. So insert ornament, based on what we did here, like the behavior of the function, we need at least three actually, arguments, and we return something. So we can define that we will return an ornament, and we are having a root.
Copilot knows you too well, but it might be that you already write this code
It knows
before.
me. It knows me quite well, but here we want to have the Linus next thing. So let's say const star, and as you see, it's already what we want to have. And now here is the tricky part. Actually, here is the function pointer. This is what David showed us earlier. So I start with the easy part, the first part, because here we say, okay, we have like a compare, and compare takes two arguments, two characters. And actually that's the idea. We want to compare a value against another value. And I mean, there is like string compare, for example, that we already know, but we could use it with something that we want to have. And this is the cool thing actually here. By saying we want to have a too easy. By saying we have here a function or a pointer to a function, the insert ornament doesn't care what it actually is. It's just relevant that it's a function actually, and this function does the rest. I mean, this is what you explained us earlier, right?
Yeah, so we just hand over a function, and inside the insert ornament function, we can call the compare function. Yeah.
When you scroll a few lines up, we can see the arguments fully. Sure.
Yeah. Sorry. We again we covered it with our
Oh,
picture.
sure.
Yeah.
What we're doing now is we insert the element by taking the characteristics of a binary tree. And what also Yulia showed you, a tree has something to do with recursion, and recursion is always when a function calls a function. And the cool thing with that is that we can use this characteristic to add a new element. And in every recursion, we create the so-called base case. Like this is the very basic case of a recursion. We define when the recursion should be over, actually. And it should be over if the element, if root is null, because then this is the very first element, for example, or the element on the position where we want to add this ornament. So we say if root is null, then then create ornament. So we have this create ornament function already, and this means if we're here, like if we created the tree, and it's null, actually the root element, which would be the case in the very first place, because we don't have, or we created it here actually. It's set to null. Then this is our first case where we say create ornament. So we create a new ornament with the name, left and right are null, and then we return this. So this is like the very basic case that we have. And if this
But I think it's a very important case because it's always in the beginning. So if we forget about this, our program will crash because it's always the first case when
and it
we
will always
create.
be our last case actually for each recursion.
Yeah,
Because what we're
true.
doing now is we say that we want to go to the right direction in the tree, go left or go right in the tree. And as we mentioned earlier today, when we add a new element in the tree, we go from an element and then we check is this less or greater than the actual value. If it's less, then put it on the left side, otherwise put it on the right side. And we're doing this now by having actually two variants, go left or go right. And the function should be called as long as we have, again, this case where root equals null. But root in that case is not like the root element at the very start of the tree. The root element can be a different element. I will just show you what I mean, and then we can discuss about that in detail. We can say here, for example, if gives me a good hint, name root name less than 0, then we go to the left, and if it's the else, which means if it's greater than 0, go to the right. We haven't defined what compare is now, but what we want to do is just have a regular string compare. We know string compare already from, or we talked about that, I think, when we talked about strings a bit. And so we just write a very basic function therefore. So it's a compare function, and this should have two arguments, name1 and name2, and then we're actually saying we have a string compare, and what we are returning is just an integer. So actually we could, for like the sake of having it still easier, use just the string compare, but we're writing a function now to make the code more modular, and then we could change some pieces in it. But since we're having now a string, this would make sense. If it would somehow change, that this name would be like a value, like an integer value, in that case, we could just modify this function here. And that's the cool thing with function pointers. Then we would also have a working compare function.
Right.
All
I
right.
have two things to add maybe. So very, very important because you have to debug a very long time if you do not know this. Str compare or str compare returns 0 if the strings are equal. This is not very intuitive from my perspective because if they're equal, it would be true in my perspective and would be 1. But str compare is a little bit different. It returns 0 when they are equal. So you have to, keep that in mind, and return a return greater than 0 if the pointer 1 is greater, and smaller than 0 if the pointer 2 is greater than, and so on. But please keep in mind, str compare, the return values are a little bit tricky. I know it because I debugged, I think, a whole weekend once. And then I found out I used the str compare wrongly. So I do not want you to fall into the same trap in this case.
Yeah, that's a very good point. Thanks, David.
And another thing is, so when you go back to the code, Alex, on my perspective, so the lines 39 to 46 are the most important thing to understand here. I know it's a little bit tricky, but this recursive call is very, very important to understand how this tree is created, because this is what Alex meant before. The first argument in the insert ornament call in line 31 and 35 is then the root left and the root right. So always the children, and they are then seen as the new root node in this recursive function call. So
basically,
this is
we
maybe
go back to that one. When we add 17, actually, this is a recursion, or I explained it already as a recursion. We want to add 17, which means we go at the root element. So this is the root element now, and we compare. And since there are elements left and right, we cannot add them already there. We have to check one of those elements. So we go to the right and say, okay, 12 is the next root. So this is the root now, and we have 11 and 15. We cannot place it here, 17. So we go to the right again, and okay, we say we have 15 here. And now we could put it on the left or on the right. And we decide, actually, since there is no element here, to put it on the right. Otherwise, we should have to do it again and go again over that. Was that what you want to say, David? Or am I?
Yeah, that's true. Yeah. So, but I think that this is just the hardest thing to understand when talking about recursion, how you give these pointers to the next recursive step, this next recursive function call.
Yeah.
And I think, again, visualizing is here the way to go for me, because then I get a better understanding. And also debug it using maybe printf or using the debugger to know how deep am I now in the recursive function call.
Yeah. Because whenever you go one level down, you will create a new function on the stack.
Yeah.
So then you can see how far you are already in your recursion. This really helps you a lot. Okay. I'm pretty fine with the insert ornament function. Dart, do you have something to add here?
No, I think that looks good.
Okay. I mean, what we could do now, we could run the function or like the program, but it might be really boring because we don't do anything. Um, insert ornament. Um, oh yeah, sure. We have to return root here. Yeah, and so we just have this one warning, which is kind of obvious. Let's go to line 73. We don't do anything with root now. Okay, what should we do now to actually get something meaningful or to actually see something? We should write some kind of a print function. And I would like to do this in the last few minutes because the print function helps us to visualize the tree and also helps us to get a sense on how the tree is like ordered in a hierarchical way actually. And so let's have a like print tree or yeah, let's call it print tree. And actually what we want to have for the print tree is the ornament. And I mean, let's try it like that already. What we have here is we have this check. If this is null, it should be returned. So recursion, obviously, because we have here the left side that should be printed, the right side that should be printed, and in the middle we have the name of the ornament that should be printed. And by that, actually, when the function is called, it is first like with the ready tree, with a tree which is not null. It goes into the print tree function with the left element first, and prints it and does it as long as it will go to this condition, and then it will return one level and continue. So it prints the name and then it continues also with the print tree. So we have actually two recursions here, one for the left and one for the right. Maybe let's just try it and see if there's something happening. No, there can't be something happening because we actually should call this function. Just say here print tree root. And now we can try it. All right. Now we have like some Can you hear me again? I think in the chat, maybe the chat. you hear me, David? Right. The chat can also hear me. Yeah. My headphones were charged for like exactly 60 minutes, obviously, or something like that. So they lost power, but I think I should be fine now. Okay. I think there are also some issues that I cannot hear you, right? But I can't hear David. So 1 second, I can also fix that. Hopefully.
Or you just finish it.
David, say something.
Yes, can you hear me now?
Yeah, I should be back. Should be back.
Yeah, okay. Yeah. What happens?
Perfect. Okay. I mean, I just want to like one or two last things. Actually, what we're having here is an ordered list. So if we compare it, we did here, what we're having here, and what we here now, it's perfectly fine ordered, like from A to B. But it's not in a hierarchical tree representation, so maybe we want to have this as well. And I will just this function in 2 minutes, and then you can also see like a nice kind of tree. So print tree hierarchy or something like that. And ideally, I take the root element and also the level, like first level, second level, and do almost the same, but just with adding two kind of symbols at the beginning that we see in which hierarchy level we currently are. So it's actually almost the same as our other print function. That was the other print function, but here we just add like two hashes to see how the tree could look like. I would say let's call it here and say we want to start at the level 0. And let's try it. And here we have a kind of tree looking thing. And if we interpret it in that way, that cookies is the root element, family is like the first, and assignment 3, they are like siblings, family and assignment 3. And then we have bananas and advent of code. And this looks actually good because everything on that side is from
smaller or earlier in the alphabet. Yeah.
Yeah, and this is after C. And if we check assignment 3, then we have advent, which is on the left side of assignment, and bananas, which is on the right side. So actually, this looks pretty good already. So we have kind of a tree, even though it's in a very weird ASCII tree representation, but actually it would be true. Or it's sorted as a tree.
All right. So one question from the chat is, what about freeing the memory and null checking the whole context? Yeah, so of course, I think null check we have done, but freeing the memory, freeing all the trees, is still open. Do you want to edit now or just copy it in?
I mean, what we could say is do it here because it's pretty easy because we can do this also in a recursive way. We just have to say if root unequals null, yeah, then we free the left, we free the right, and then we free the actual element. So we call the left, we call the right, and then actually free the root element. And this should do the job actually.
Yeah. And this is not that much code, and that's the cool thing with recursion.
Yeah.
The downside here is that it's pretty hard to understand. And if, of course, Alex prepared it a bit, and it's always the same if you're creating trees, but it might be tricky to understand and to find errors if you have an error somewhere. So it's a cool way recursion, and you definitely should try it. But it really depends on the context. So in many cases, in my opinion, loops are the better choice. And yeah, binary trees are one of the go-to cases where you should use the recursion, in my opinion.
Yeah. So overall, I think we talked about this last week, and Julia also mentioned that there will be many applications where you will use trees because they're pretty handy for some situations, but it requires a certain experience using trees because it can be quite tough. And I always like also when I prepared the today's lecture, I started by actually sit down and started with drawing a tree, thinking it through. This like requires some drawing to like get a sense on how the tree should look like, how you want to do things in the tree. And there are like billions of implementations. This is like one possible implementation. You could do also other things as well, play around with that. But yeah, you won't need the trees for the assignment 3. But it's a data structure which is really handy, and I mean, it's possible that there might be an exam, like a Surbeispiel, like exam task with a tree, but usually then it would be very easy to, because we know that during an exam it also requires some like cognitive flexibility to as well.
Yeah.
All right.
All right.
I mean, there was also a question in the chat if you are allowed to use Copilot. We have a clear policy on Copilot and ChatGPT, so check the course website. You will find all the information there. Honestly, today there was more like I have Copilot installed and I forgot to deactivate it for programming. I mean, it would deactivate it, but I mean, just for all of you who never saw Copilot, then you've seen it now. But I think in other courses, also you are allowed to use it, or at least to a certain degree. But yeah, you see, it's quite handy here, and I mean, it has to do with the fact that I have this tree file open where I implemented everything already. So Copilot was a bit inspired by my other file that I prepared. I will upload.
And it's not that accurate all the time.
It's not that accurate all the time, and especially when it comes to the assignment interviews, then you of course have to also know what you did actually, even some. Okay, I will upload the code at our course website again. I also added some function headers here, so we'll get like the cleaned up and nice version. also like with some comments in it. Then you can go again through it and get a sense on how to build the tree. Okay. So David, I think it's time for us actually now to close the lecture for a very last time.
Yeah. So it was a very, very interesting semester. So for us, the semester of the lecture at least is over. Of course, the practicals still going on. So enjoy your Christmas, but also do not forget about assignment 3. Of course, there's much to do. But if you have any questions, of course, the tutors and also we are happy to help on our Discord server. And yeah, so happy holidays from my side. Anything to add from your side, Alex?
No, also not from my side. Happy holidays, everyone. Try to enjoy like the Christmas break. I know break is yeah, assignment 3 is there already, and I'm sure you have other things to do as well. But at least some days to like relax a bit and spend time with families and friends. Yeah. There was this question in the chat also if we know if we can correct it till Christmas, like the exam from Tuesday. I don't want to promise anything today because I mean David and I we're both sick currently actually.
Yeah.
Actually the lecture was also very spontaneous today because both of us are not very fit currently. So let's see if we can manage to do this, and we have also some other things get done before Christmas. We will give our best, but I cannot promise you. And usually we have the rule to not give it like too close to Christmas because we don't want to interrupt your like happy Christmas celebrations, and so probably a bit after Christmas. But I think
yeah.
But
yeah, I think that sounds good. That sounds doable for us. Yeah, thank you for all the wishes in the chat. Was very, very nice this semester, and hope to see you soon in latest next semester then in object-oriented programming.
All right.
Great.
Then,
then.
Good evening. Nice
Thank you very much.
Break, and yeah, we stay in contact over Discord. See you.
Yeah.
Bye.